Okay, this is lecture 6. And so this happens to be Merkel-Hellman right here. That's what their actual formula is. Do you like these little pictures I found? Okay. In my opinion, Hellman is actually a darn good mayonnaise. Do you ever have Hellman's mayonnaise? It's the best. It is you have to use mayonnaise on some things. Hellman's is the best. Yes, it is. You always, okay, Hellman is the best. So if you don't agree with that, you can drop now. Okay. So how it works, we pick a simple super increasing knapsack. We know how to do that. That was simple so far. Then we calculate the hard knapsack and we encrypt the message. That's all there is to it. Simple. Okay. There it is. Gets a little more difficult. So a receiver picks, so Brett back there picks a simple super increasing knapsack. Okay? Okay, he also picks the multiplier and the n. So N or S, W, and N. Okay? So Brett happened to pick 1, 2, and 6. Is that super increasing? So 2 is bigger than 1. Is 6 bigger than 2 plus 1? So we're good. We got a simple super increasing knapsack. Now we have W of 11 and N of 13. Okay? They're usually all prime. For some of my examples, they're not, but just go with them because they're just examples. Okay? In the real world, these are huge numbers. So the receiver computes, in other words, Brett is going to compute the hard knapsack and send it to me. The general form, which is what this line is here, the general form of the hard knapsack is W times SI mod N. In other words, W times the first value for S mod N becomes the first value for H. See how that works? So W times the first value for S mod N becomes the first value for H. W times the second value for S mod N becomes the second value. W times the third mod N becomes the third. Everybody see that? So 11, which is W, times 1, which is S1, mod 13. Let's talk about this. We haven't covered this yet. 11 times 1 is 11. So far, so good. Modulus is the remainder. Okay? In other words, I need my awesome pen skills. Everyone remember back in elementary school when you did long division? Okay? So, we're on this first one right up here. So you take this 13 and put it in front of the 11. So if I have 11 right here, we take the 13, we put it in front of it. Then we perform long division. How many times does 13 go into 11? 0. What's the remainder? 11. Have I seen that? How many times does 13 go into 22? Remember, we put the line here, put 13 in front of it. Okay, it goes in once. So 22 minus 13 is 9. So the remainder is 9. So the modulus is the remainder. Everybody seen that? It's not tough. We're talking elementary school math here. So we take the 13, put it in front of the 66. It's very critical you get this part. Let me tell you why it's critical. Because see this 11 mod 13? The answer is not 2. So many times people will say that's 2. I've done it. It just looks wrong to be 11. See what I'm saying? It looks wrong. So the answer is 11. Because the 13 goes in front of the 11. How many times 13? It doesn't go in 11. So what are you left with? 11. It's not 2. Okay, so many times people do that. It's like, no, dude.
Either 2 or 0
Right.
based on.
Right. So 13 goes into 66. What? 5 times 65. Yep. 5 times. So 13 times 5 is 65. 66 minus 65 is 1. Remainder is 1. So our hard knapsack is 11, 9, and 1. Easy enough? Simple dimple, isn't it? That's super easy. Okay. So the receiver, Brett back there, now sends me 11, 9, and 1. Now, if you think about it, do I know what he started with? Do I know the simple knapsack? No. I don't want to know it. He needs to know that. So he sends me the hard knapsack, and he keeps the simple knapsack N and W secret. Okay. Now I want to send him a plain text message. My message happens to be 101.010.0.011. So I multiply my hard knapsack 1191 by those values. So I just repeat my hard knapsack over and over and over for each of the values. So 101, 010, so 11 times 1 plus 9 times 0 plus 1 times 1 is 12. 11 times 0 plus 9 times 1 times 1 times 0 gives us 9 and 10. So our ciphertext is 12, 9, and 10. So now I can send Brett 12, 9, and 10. So far so good? So modulus. What's 8 or 33 mod 8? So 33, 8 goes into 33 4 times for 32. Okay? So, and the answer is not this. This is not the answer. Remember, you put the 8 in front. You take this 8, put it out front here, divide it here. 8 goes into 33 4 times. 8 times 4 is 32. Subtract them, you get a 1. Okay? Remainder of 1. Easy enough? Just you got to remember that, because I'm telling you, you're going to do it wrong. I know you're going to. Okay. Now we need to calculate the multiplicative inverse of W. I'll show you 3 different ways to do it, and we're going to run out of time. That's okay. This is method 1. You're going to have to do it all 3 ways. Okay? N is 13, W is 11. We need to calculate the multiplicative inverse of W. It's not, I mean, if you look it up on Google, it's not quite done this way, but this works. Just do it this way. So the multiplicative inverse of W is, method 1, W raised to the n minus 2 mod n. So in this first example up here, n minus 2 is 13 minus 2. So it's 11 raised to 13 minus 2. What's 13 minus 2? 11. So it ends up being 11 to the 11th mod 13. 11 to the 11th is this big old long number, mod 13. Now, if you have a Windows machine, you can actually go in here, and if you change this to scientific or programmer mode. No, it's scientific mode. Whichever mode it is, I can never remember. So then if we did 11 mod 11, I'm sorry, that's not mod, 11 raised to the 11th power, we get that big old long number. Then we can do mod 13 equals 6. I will tell you, some calculators can't handle these larger numbers. Some of the numbers on your assignment ain't going to work. But you have to figure that part out. So the multiplicative using method 1 is 6. Everybody see how that works? Pretty simple so far. So it's W to the n minus 2 mod n. Here's method 2. This is actually really the best way of doing it, but the comparison method. We make 3 columns. Column 1 is n, column 2 is W, column 3 is going to be comparisons. So we start with 1, 0, 0. You just have to remember this. You're going to use this as another way as well. So n is 13, W is 11, comparisons. So we start with 1, 0, 0, so it's 1 plus 13 is 14, plus 13 is 27, plus 13 is 40, so on and so forth. 0 plus 11 is 11, plus 11 is 22, so you keep going down. You're looking for matching numbers. And wherever they match in the W column, go over to the comparison column, and that's the answer. Do not give me a 5. Wrong. Okay? So wherever they match on the W column is the answer. Everybody okay with that? I mean, it's pretty simple. Very, very simple to do. You can make Excel spreadsheets to do this. I wrote a Python program to solve all these so far. Did everything except des and AS. Super easy to do. Here's a third method. Okay. This time we're just doing with W to the W. Where'd my marker go? W to the W right here. W in this case is 11, so 11 to 11 mod 13 is 6. The answer is 6. Easy enough. Now just so happens that method 1 and method 3 end up being basically the same because it's really 13 minus 2. But that's just for this example. It's not always that way. Now for your assignment, you have to do this multiple times. And they're not always the same answer. In this one, they all worked out to be the same. For your assignment on this, they're not always the same. Okay. So now how do we decrypt a message? We already did this. We already calculated the hard knapsack. Remember, it was W times S mod N. So the first S became the first H, the second S became the second H, so on and so forth. Okay? So, this right here, H times P, hard knapsack times plain text, mod N. This is again from the previous slide. You can go look at it if you want. We just did it. But basically the math we're looking for is this, right there. That's the real math you need to know. Okay? So let's see how this math works. We take the multiplicative inverse of W, which in all three examples happens to be 6. We just did that. Okay? It's also right here. 6 times our ciphertext, and in this case our ciphertext is 12, 9, and 10. So 6 times 12 equals 72. Mod N, which is 13, gives us 7. Okay? That's not the answer. Some of you are going to submit that as your answer. That's not the answer. That's the intermediary value. Okay? The plain text is not 7. Remember we started with a binary value? We need to get back the binary value. So with this here, because remember I sent Brett the ciphertext. Brett is going to be using the ciphertext along with the multiplicative inverse of W. Which I lost my marker. There it is. So he's going to use the inverse of W and the ciphertext to come up with his 7. Then he's going to look at his simple knapsack and say, what combination of these values equals 7? 1, 0, 1. So he's going to use the multiplicative inverse of W, the next ciphertext, which is 9, because that's the 54 mod 13 gives us 2. So what combination of 1, 2, and 6 gives us 2? 0, 1, 0. Then we got a 10. 6 times 2 is 60. Mod 13 gives us 8. What combination? That would be a 0, 1, 1. So it's the 2 and the 6. It works easily. Very easily. A lot of steps. But you see how it works? Yes? Easy enough? Here's an example. Compute the hard knapsack. I'm not going to give you this line right here. You're going to have to remember this line right here. You're going to have to remember this. Okay. So remember, S to the I mod or times W mod N, or you can switch these back and forth. It doesn't matter. It's just math. So we had 1, 3, and 6. So 1 times 11, 3 times 11, 6 times 11 comes out to 11, 33, and 66. Mod 13, and we get an 11, 7, and 1. Are we okay with that? Very simple. There's no special math there at all. But just remember, these things go in the front. This numbers all go right into the front. We put our little division symbol on all these. Okay, whatever that is, I don't know. Okay. Okay, encrypt this number. So we take our hard knapsack, we encrypt our binary plaintext message. So we had the hard knapsack from the previous slide, 11, 7, and 1. We encrypt 1, 0, 1. So 11 times 1 plus 7 times 0 plus 1 times 1 gives us a 12. And then a 7, and then an 8. So far, so good? Everybody with me? Then decrypt. Okay, we've got to calculate the inverse of W. Unless I tell you differently, okay, all three methods will all be the same, except for the homework where you're only calculating those. When you have to do this, I'll tell you which way to do it if they're going to be different. Okay? So, found out the inverse of W. Then we take our Wherever my mouse went? Where's my mouse? Oh, it's up there. Okay. So 6 times our ciphertext mod n. So 6 times 19. Remember, our 19s are ciphertext mod 13. Gives us 10. Then what combination of our simple knapsack up here, 1, 3, and 6, gives us 10? Do not submit 10. I'm telling you, you're going to. It's not. Remember, the answer is always in the binary. So what combination of 1, 3, and 6 give us 10? I know you could just add them up, but you need to know the math behind it. Okay, so 1 times 1 plus 3 times 1 plus 6 times 1. So 1, 1, 1. Over here, 6 times 18 mod 13 gives us a 4. What combination of 1, 3, and 6 gives us 4? That'll be 1, 1. 1, 1, 0. Easy enough? It's very simple. There's nothing difficult at all. Just a lot of steps. Okay? The modulus, the n, is normally 200 digits long, 200 bits long, so it's very huge. The simple knapsack are actually usually chosen 2 to the 200th apart. So it's not 1, 3, 6. Imagine those numbers being 2 to the 200th apart. They're normally 200 digits long, and they're normally random numbers. So numbers are huge. Each term is normally 2 to 400 bits long. It'll take 10 to the 47th year to try them. It's hard to break for large values of n and m, obviously. Okay? Shamir in 1980 found a weakness in it. It says it's possible to determine the simple knapsack in polynomial time. In other words, it might take forever, but you can determine it. And he proved you could. Okay? And here's what the test will look like. Exactly like this. Okay? That's the end of that one. Oh, I got through all of them. Sorry, I went a little quick.